Okay, here is an Alex question dealing with Lewis dot structures, seeing if these are reasonable or not, and let's see if we can't answer some of these. Okay, so the first one, this has 3 Lewis dot structures that is being asked if this is reasonable or not, and if it's not reasonable, then it's asking where are the problems. And so I have to write these down. I just can't look at the structures. I just kind of have to do them myself and then go back and answer the question. So let's take the NH2 plus ion right here. And so let's come back here and see if we can't do this. It's asking us to do NH2 plus. Okay, so first thing I always do is count up the valence electrons. In nitrogen, then there are going to be 5 electrons. In each of the hydrogens, there is 1 electron. So I've got 2 of those, and so this is going to be a total of 7 valence electrons, but we have that plus charge, so we're going to subtract 1, because that's what a plus charge means, that we've lost an electron. So I have to account for 6 total valence electrons. Alright, let's go ahead and start drawing the basic structure here. So we have NH, H. Alright, the H's are completely filled up. You know that those will only have 2 valence electrons around each one of those. And so I have my bonds there, so I've accounted for 4 valence electrons, because each of those bonds has 2 valence electrons. So it's going to be 6 minus 4. I still have to add 2 more valence electrons. And so I can only add those to that central atom right there. And so this would be the reasonable structure for Lewis dot structure for NH2. And then because this is an ion, then I'm going to have to make brackets around it, include that plus charge. So for NH2, this is the reasonable Lewis dot structure. It does violate that octet rule, and that's kind of what we're studying now, our violations. So let's go back here to this, and so as we look at our structure, we see that there are 2 double bonds around that hydrogen, and that doesn't work. So if I count up the valence electrons, this has 2, 4, 6. So that one is correct. There are the right number of valence electrons, but no, some of the atoms have the wrong number of electrons around them. And the symbol of the problem atoms are that hydrogen. That's the one that is going to be a problem. Okay, so that's how I would tackle that first one. Let's look at the second one for SF3 minus. Okay, so let's just go back and go ahead and draw that. Alright, so now I have the SF3 minus ion right there. Alright, so let's go ahead and count the valence electrons. Sulfur, there's going to be 6, plus there's 7 in fluorine, but I've got 3 of them, so it's 7 times 3. And then I've got that 1 that's in the ion that's going to be plus 1. And so in this case I have 21 plus 6 is going to be 27, so plus 1 is 20. I've got to count for 28 valence electrons in this particular ion. So let's just go ahead and draw the structure here. So I've got S, F, F, F. I've got those 3 fluorines right there. Okay, so let's go ahead and now complete the octet around the fluorines. Let's go ahead and complete the octet around those fluorines. Almost there. Okay, now I believe in the structure that was proposed, they actually had a double pair right there. Okay, so let's just go ahead and look at this and see if we're right. So around each of the fluorines there are 8 valence electrons, so 8 times 3 is 24. Okay, so 24. So I've got to count for 4 more electrons somewhere in the structure they proposed. They had 2 more valence electrons right here, which would be a total of 26. But we know we have to have 28 valence electrons. And so what I would do for this Lewis dot structure is go ahead and put another lone pair around that sulfur. Now yes, that does violate the octet rule, but if we go back and we just glance at our periodic table here, then we see that sulfur is located down here along this third period right here, which means that we can occasionally violate that octet rule. And that's exactly what's going to happen in this case. The fluorines cannot violate that octet rule. I can't expand those octets at all. And so let's go back and answer this question. Is this a reasonable structure? It is not. The total number of valence electrons is wrong. And we already calculated that 28 is the right number of valence electrons. Okay, let's go down and do this IBR2. And so let's just again go back to our page here where I can write. And so this is IBR2. Very good looking B. Let's scratch that. IBR2. And that's going to be a minus charge right there. Just let me double check and make sure that is the case. And that is the case. Okay, so let's come back here and let's finish drawing this. Okay, so let's count up the number of valence electrons that I have here. So that iodine has 7. Each of those bromines also have 7, so a total of 14. Plus that 1 that forms that charge, so there's 22 total valence electrons that I have to account for. Okay, so let's go ahead and draw our structure. We have I, we have Br, we have Br. Let's go ahead and complete those octets. Go ahead and complete those octets. Okay, so we have those valence electrons accounted for. Now let's count up how many we have here. So I have 8, I have 8. And so that's going to be a total of 16 valence electrons that I have drawn into my structure so far. And so I need 6 more. All I can do is put those on that central part. So I've got 2, 4, 6 is how I'll place those around. Go ahead and put that into a bracket with that minus charge right there. And so this then would be a valid and correct Lewis dot structure. So let's go back and finish answering that question. So as I look, it's exactly what we've drawn. So yes, that is a reasonable structure. And so I should get this problem right. And so let's go ahead and click on check right here. And it's come back and told us that we are correct. So that's how you tackle these problems. I know we try to do these in our head, but I just can't do it in my head. I actually have to draw the Lewis dot structure and then compare it to what they drew.